Hi, my name is Eugene Lee, and this is my Physics 2212 Lab 6 report. So to start off, the purpose of Lab 6 was to investigate the interaction between a falling magnet and a row of aluminum foil both experimentally and computationally. The models and fundamental physical principles used was the principle of magnetic induction, the equation for the magnetic field of a dipole, Faraday's law, and also Newton's second and third laws of motion. As a brief preview of results, it took 0.919 seconds for the magnet to fall through the tube in our experiment, while it took 1.51 seconds for the magnet to fall through the tube in our computational simulation. And here's a little bit more about the science behind the experiment. As the magnet falls through the tube, because the tube is a conductor, each section of the tube will experience a change in magnetic flux, and that induces a current which then generates its own magnetic field. The tube and the magnet are arranged in such a way that the top portion of the tube will attract the magnet upwards, while the bottom portion of the tube will repel the magnet upwards. These effects combine to create a repelling force that slows the magnet down as it falls through the tube. For the system and surroundings, the system was the ball magnet in the aluminum tube, while the surroundings was Earth and other nearby objects. The initial condition is that the ball magnet is stationary and held just above the entrance of the aluminum tube. And here's a video of one of the trials of our experiment. You can also see the rest of the data that we gathered on this slide. After summing up all the trials and averaging them, we found that the average time for the magnet to fall through the tube was 0.919 seconds. And here's our computational simulation and the code that I wrote for it. All of this code basically just sets up the simulation, generating things like the physical constants, dimensions of the aluminum tube, and also the ball magnet properties. Then this section of the code calculates the magnetic field at any point in space due to a dipole, while this bottom section here calculates the change in flux for any given piece of the tube. Then this is the most important part of the code. It calculates at each time step the force of gravity and also the flux / EMF due to each ring and also the current that gets induced from that. It then calculates the total net repulsive force and then uses that to calculate the net force on the magnet. And we can then use that to derive the acceleration of the magnet, its velocity, and therefore its position. Here's a video of the simulation in action. As you can see, it took around 1.479 seconds for the magnet to fall through the tube. You can see that this straight line in the middle represents the terminal velocity, which is when the force of gravity equals the repulsive force. And this initial decrease in velocity with this dip right here represents where the magnet has not yet fully entered the tube. And then this dip right here represents when the magnet is in the process of exiting the tube. So for some similarities and differences between the experiment and simulation, in the simulation we assume that there was no air resistance, that the magnet falls straight down, and that there is no interference from other magnetic fields such as Earth. However, all these factors would make the calculated simulation time be less than the experimental time. So the fact that it's greater must mean that there weren't significant factors. Probably the biggest source of error is a wrong magnetic dipole moment, since we used the value that we calculated in the previous lab, and then that probably itself had a lot of errors in it. Since the time it took for the magnet to fall is actually greater than what was calculated, then the actual dipole moment must be less than what we used in this lab, since force is directly proportional to the moment. Some possible sources of error in this experiment included the fact that our timing was not perfectly accurate, because it's hard to tell when the magnet exactly enters / leaves the tube. Another source of error could be that we didn't perfectly measure the tube's dimensions, and that the tube might not have been held perfectly straight. Now to answer the what if questions, if the resistivity of the conductor was reduced to as close to 0 as possible, that would cause infinite current in the tube, and infinite current would then mean infinite magnetic field. That then leads to a very strong opposing force, meaning that the magnet essentially becomes stationary in the tube. Then if holes or slots were cut into the tube, that would mean that current would be unable to flow through the ring in that location. Therefore, this is essentially equivalent to an increase in resistance because there's less current, so that causes a weaker magnetic field and therefore a weaker opposing force. So the magnet would fall faster through the tube. That's it for this lab. Thanks for watching.